thanks to the organizers for the invitation, and it's nice to be back here in Philadelphia. Yeah, I guess maybe the first thing we should do is maybe I switch things up a little bit. So the first half of that title, I think, is still correct. It is the mighty Laplacian and Symmetry. I think that makes a whole lot now. Applications of there. Okay, so we'll see what we do. Okay, so yes, I guess the idea is to kind of just maybe give everybody like an introduction to spectral geometry. I suppose like maybe like sure.
You get an on, there's like a switch at the top. I think so.
Yeah.
I think so.
Okay, all right, so that's all started. So yes, so the title is, I guess it's now Laplacian and Symmetry, Applications of Heat Invariance. Yeah, the idea is for this to be a sort of an introduction to spectral geometry, which I suppose allows you to explain to people just sort of, metaphorically is like a following game. Let's suppose like I have a drum behind a screen, and you guys have materials from which you can build a drum. And the idea is I'm going to play my drum, based on what you hear, your job is to build a drum that sounds exactly like mine. So for the purpose of this experiment, we'll assume that you're all expert drum makers, and you also have perfect pitch. Okay, I play my drum. You guys, this is not me. I see the track. Okay, see if that's safe here. Okay, and so I'll play my drum, and basically you're going to build a drum that sounds like mine. So we do all this, and then the question really interesting, when I lift the screen, what really interesting is, well, in order for your drum to sound like mine, there were certain geometric properties that were forced upon you. So does your drum have to, let's say, volume or surface area, maybe some certain curvature properties in common. So this is, I guess, this came in the shape of a drum problem. I guess in terms of what this is mathematically, so we can sort of formulate it this way. We'll let omega, we'll start in the plane, just be a bounded domain. And we're going to assume that this is kind of like, I guess, the boundary, or I guess it's the drum head. And the idea is it's going to, when we strike it, it kind of vibrates in the direction which is orthogonal to the board. So we'll kind of let this function u of x, y, t equal the displacement of the point x, y at time t. And so the point is that, okay, well, u has to satisfy it's in this wave equation. And so that's just the second partial of u with respect to time plus delta u is equal to 0, with the boundary condition that u is going to be 0, so the edge of your drum head is fixed. And this is where we take the Laplacian, and I'm going to take a negative sign in front of my Laplacian, so it's the Laplace operator. Okay, and so the point is that the Laplacian is a self-adjoint operator, so it has a spectrum. So self-adjoint. And so we'll let its eigenvalues sort of be known as the spectrum of this domain. So we have 1, 2. Okay, so it's a sequence of non-negative eigenvalues flying off to plus infinity. And so, as you know, probably from teaching in differential equations class, or if you wanted to solve this wave equation, you apply the method of separation of variables. So we assume that your function looks something like this. It's a product of something in time, and then a product of something which only depends on the position. And then, of course, then you end up getting that your general solution looks something like this. And this is all times k. And this is where the Laplacian of p sub k is equal to lambda k p sub k. So, all right, so these are, I guess, this is the general solution to the wave equation. And in order to solve it, we see that this eigenvalue problem pops up. And so, I guess, since we're talking about drum heads, we sort of have a right to basically interpret these eigenvalues as basically determining sort of natural frequencies at which this drum head will resonate. So we get here that you can write the spectrum of our domain is equivalent to the sequence, let's say f sub k of lambda k divided by 2 pi. Okay, these are the natural frequencies. Okay, so on some level, we can think of, let's say, the lowest eigenvalue here is, let's say, like your fundamental, and then all the other eigenvalues are basically like your overtones. And so I guess then the question only becomes, okay, if you know the sequence of eigenvalues or the natural frequencies at which this drum head will vibrate, what can you say about the geometry and sort of vice versa? So, problem. I guess we want to explore relationship on one hand with the geometry of omega, and on the other hand we have the spectrum omega and other spectrum pattern. Okay, when I say other spectral data, I'm also including, let's say, the eigenfunctions in this as well. So one might also want to know things about how the geometry of the domain, what does that have to tell you about the eigenfunction that you have, and then maybe vice versa. One can also be concerned with that. Okay, so I guess the foundational question would just be, along with the metaphor that has, well, okay, if you had two domains with the same spectrum, do they actually have to be congruent to each other? So let's see this question. So R2, let's say isospectral. So two spaces that have the same spectrum, called isospectral. So two isospectral domains. Necessarily symmetric or congruent. Okay, so I guess to see that this question might have some merit, the thing to note is if I look at the sum of e to the negative lambda k t, okay, well, this actually converges for all positive t. It gives me a nice smooth function on the positive real line. So this guy is a smooth function on the positive reals, and we simply write this as the trace of e to the t times our Laplacian. And what we can notice is, so the game in spectral geometry a lot of times, if you're trying to sort of prove positive results, is to sort of take some kind of spectrally determined function or distribution more generally, and see if you can say something, if like studying the singularities of that actually somehow tells you something about the underlying geometry. And so it was observed, I guess back in the 60s, okay, that this trace in this particular setting has an asymptotic expansion as you approach from the right-hand side, where you get the volume of your domain divided by 2 pi minus the length of the boundary divided by 4 times the square root of 2 pi times t. All right, so that tells us right there that there already is some geometric content in the spectrum. So on the left-hand side, you have something which is completely determined by the spectrum. On the right-hand side, you have some geometric information. So we know that two domains that have the same spectra or the same natural frequencies in which they resonate have to have exactly the same volume. They also need to have exactly the same boundary length. So, okay, that seems like we're maybe off to a good start. However, it turns out that it's not true in general. So, this exactly, or I don't know how you feel about one. Turns out there are, I suspect, planar domains that are not. Isometric. And so this was maybe first established by Gordon, Webb, and Wolpert in the 90s. Except here, I guess the point is these, what their examples don't have smooth boundary. Okay, so they have these like domains, which I'll get wrong if I try to do, but okay, anyway, they have piecewise, linear boundaries. This is not what the domains look like, but anyway, there are things that look like this. You can put down two of these guys in the plane, and it turns out they actually have the same eigenvalues, they have the same volume, they have the same boundary length, but nevertheless, they're not actually congruent to one another. All right, so, okay, so that's, I guess, the problem in 2 dimensions. So what I want to do is, I guess, maybe talk about this problem more generally on compact harmonic manifolds. So I'll define what I mean by the Laplacian in that setting. We'll see the ultimate spectrum, and then we'll kind of go from there and see what kind of information we can learn. Okay, so the general setup. Okay, so I'm going to let MG be a compact harmonic manifold. And here we can define our Laplace operator just to be the negative, the divergence composed with the gradient of the vector field. That takes you from your smooth functions into itself. Okay, so the gradient obviously telling you the direction of steepest increase for a particular function, and then the divergence is telling you, I guess, how the flow of a vector field distorts volume in this given area. So composition, and once again, I put the negative sign in here because I want my spectrum to be non-negative. And so then if the boundary of M turns out to be non-empty, we impose boundary conditions. And so there's what's known as the Dirichlet boundary condition, which is that on the boundary we want it to be 0. And then there's the Neumann condition, which says that we want the normal derivative along the boundary to be 0. Okay. And so when we do this, if you have the non-empty boundary, then you actually do get a self-adjoint operator, and you can apply spectral theorem, and everybody's happy. So if you don't have a boundary, we don't have to worry about this. And for most of this talk, I'll be talking about spaces that do not have boundary, except for when I actually need to draw some features or something like that. Okay. So we get And so once again, we have a spectrum of the space. And okay, so when I'm dealing boundaryless manifold, I have a zero as a non-trivial eigenvalue of the spectrum. And so once again, just like an analogy with what we're doing in the planar domain case, you can think of these as, let's say, the natural frequencies at which this more generalized from head likes to migrate. So I guess in the title, there was this idea of the mighty Laplacian. And so I guess what I want to convince you is that, okay, well, the Laplace operator shows up in lots of settings. And in each of those settings, these eigenvalues and eigenfunctions kind of take on different interpretations that have sort of proved to be useful in mathematics and physics and other areas. So we've already seen that we have the wave equation. But another thing we could try to model is, let's say, I guess heat. Well, let's start with Schrodinger. Actually, how a free particle might engram inside a manifold. So here, so this is what's in Schrodinger's equation. Okay, well, you were saying this is modeling, so you have some particle with quantum level, so there's a particle, free particle in this manifold, and it's governed by this differential equation. And I'll come back a little bit later and say a little more about how we interpret the eigenvalues and the eigenfunctions of this. And then another equation that we have is the so-called heat equation. Okay, so these are maybe the three of the main equations that show up. And they all have solutions that are bound by doing that separation of variables trick. So the general solution to this looks something like this. So our function u x t, well, it's going to look like the summation from k equals 0 to infinity of some constant times e to the I square root lambda k t times e sub k, the wave equation. For Schrodinger's equation, we get e to the I lambda k of t. Okay, this is Schrodinger. And then finally, for the heat equation, okay, and this is where the phi sub k's satisfy our eigenvalue problem for this particular manifold. Okay, and I'll assume, let's say that this is an orthogonal basis. Okay, so I have an orthogonal basis of eigenfunctions. I can write down my general solutions. And what I'll note here in the case of Schrodinger's equation, one way of interpreting these eigenfunctions, they're actually giving you sort of probability densities on your space. So I'll explain what I mean by that. So here, I guess, so for Schrodinger's equation, we have that if this guy is a unit length eigenfunction, well, then what I can do is I can look at the integral of its norm space. And this probability density, this is now telling you the probability of finding this free particle in the set A. All right, and so under this interpretation, we're thinking of the eigenvalues as, like, say, the energy levels, and the P's are now giving these probability densities. And so then one of the things that one might also consider in spectral geometry, so what happens in what's called the high energy limit? So as you let lambda go off to plus infinity, what is happening with these eigenfunctions? And so if you've taken this or heard about these things before, okay, you may have heard about this correspondence principle, and the whole idea is, okay, well, in this high energy limit, somehow quantum mechanics is supposed to be sort of converging to classical mechanics. And so that what this means is that as your energy levels are getting higher, or as the scale of your system gets large relative to Planck's constant up there, that your eigenfunctions should start to reflect somehow classical mechanics. So one of the things that you might expect is that as lambda is going to infinity, let's suppose you had an ergodic geodesic flow on your space. Okay, so the geodesic flow is like the classical dynamics, Hamiltonian mechanics. So then in the limit, what you might expect is that, okay, that flow starts, these probability measures start to sort of equidistribute over the space, reflecting the fact that the underlying classical system is actually a chaotic system in the sense that it's ergodic. So I'll just put that down. Okay, so here, because the correspondence principle was that quantum mechanics what's called the semi-classical limit goes to classical mechanics. And so for us, what this means is that these measures P, and then it goes to plus infinity, I guess start to reflect the underlying classical, well, I guess we should say the underlying geodesic flow. Okay, and so some of you might then come to encounter talks about, say, it's called quantum unique ergodicity, things like that, but that's essentially where that problem falls, like into this box over here. So let me just summarize then on what I really want to talk about. Just our interpretations. So here we have our Laplace eigenvalues, and here we have Laplace eigenfunctions. And we have these three different equations. We have the wave equation, Schrodinger, and then the heat equation. And so then, I guess the point was that, okay, in the wave equation, these were interpreted as the natural frequencies. Of the membrane. And the eigenfunctions give us the shape of that particular mode. In Schrodinger's equation, we get these are, I guess, energy levels of a free particle. And the eigenfunctions give us the probability densities. And then in the heat equation, the eigenvalues are giving us, I guess, the diffusion rate. So here we're modeling how heat distributes itself in the manifold over time, as lambda k's are telling us how fast the heat is distributing, and these eigenfunctions are sort of initial heat distribution. Okay, so those are some of the things that show up in, oh yeah, sorry. Yes. Oh, yeah, so these are, right, so I'm saying these equations give you different interpretations. So the eigenfunctions are all the same, right? So there's the eigenvalue problem. But then when I'm solving, let's say, the heat equation, okay, well, or if I'm solving, let's say, Schrodinger's equation, I can have these different interpretations of what these eigenfunctions actually mean. So, yeah, so, right, so, but yeah, so it's the same, this problem doesn't change. The only thing that might be changing is what equation am I trying to solve. So you get the same eigenvalues, the same eigenfunctions, but the solutions are just kind of put together in different ways. And then when you do that, these things mean slightly different things. Yeah. So, okay. So maybe we'll, I guess, from this we see that eigenvalues and eigenfunctions are somewhat important, so maybe let's do like a few examples of like computing some of these guys, and then we'll get into this heat variance. So, okay, so one example would be, let's say, let's take a torus. So here, we can like Tn equal Rn by gamma, where gamma is some lattice, a full rank. And then we'll let gamma star be the dual lattice. So you have Rn, you have the usual flat metric on it. We can mod out by some lattice. And okay, we can now talk about this eigenvalue problem there. And so it turns out that your eigenfunctions and eigenvalues can be read off fairly easily. So here we get that our eigenfunctions are linear, well, are just given by so these guys turn out to be eigenfunctions of the Laplacian on the torus, and they have the corresponding eigenvalue 4 pi times the norm of gamma star squared. These are the eigenvalues. And so here you can then see that an eigenvalue is going to occur with a multiplicity according to the number of times. So if I pick a value lambda, I'm really asking myself, well, how many times does a circle of radius lambda intersect the dual lattice? So this is now the little, this is the circle. So, so the multiplicity. Let's see here. Equals the number of points in gamma star on a circle of radius lambda. Okay, so there we can actually get explicitly the eigenvalues, and we also have a basis of eigenfunctions, so we can write down the solutions to those equations explicitly. Another example would be, let's say, like a sphere, just a round sphere. Okay, well, in this case, we have our space of homogeneous polynomials. Of degree k. And so then here in this case, we can see that our eigenvalues are going to be given by lambda k equal to k times equals a minus 1. And then what we do is we just take the polynomials in this space and just restrict them to the sphere. And those will all turn out to be eigenfunctions with this particular eigenvalue. And then the multiplicity of that eigenvalue is exactly the dimension of this space. So this guy is equal to n plus k, choose k, minus n plus k plus 1. Okay. So what we're seeing here in these examples, okay, so these are the examples will be computed, and they all have explicit eigenfunctions you can write down, and we also see that they have actually incredibly large multiplicities. The point is that, well, typically we can't actually write down the eigenvalues and eigenfunctions for a typical manifold. So here what we're really doing is we're exploiting the presence of symmetry in this problem. And so I'll just write down the general principle, since I guess this is also algebra. So I guess more generally, let's suppose that G mod K is a symmetric space, let's say irreducible. So what I can do is I can look at the space of representations that have non-trivial k-fixed vectors. So what I'm saying is sort of take an irreducible representation of my group G, and there exists some V inside here, not equal to 0, such that for every K inside K, K fixes that element in the representation. So then, for those who exposed to representation theory, you'll know that okay, your representations are given by indexed by highest weight vectors. And so the point is that I take with highest weight lambda, then oh, maybe we should call that mu, sorry about that. Then the corresponding eigenvalue is given by this expression where rho is equal to half sum of the positive roots. So I'm not writing this down expecting everyone to know what this means, but just to say that if you find yourself in this situation where you're dealing with symmetric spaces, one can actually appeal to algebra to actually compute all this. That's maybe the takeaway from all of this. And on some level, okay, obviously, towards not an example of the irreducible symmetric space, but like the sphere is an example of an irreducible symmetric space. And here, one can actually apply this principle here to get exactly that answer over there. So that's one way of getting at it. So pick your favorite irreducible symmetric space, maybe like a CPN or something like that. You can go through this sort of yoga and compute its spectrum and its eigenfunctions as well, very explicitly. But unfortunately, this is highly non-generic. So I guess in general, so one might want to sort of go through and okay, can explicitly compute these things and just compare computation to show that things are not actually equal to each other. So we have to be a little more indirect. We actually want to get somewhere when we're looking for a spectral problem. So, okay, so to make progress on this problem, we actually need some what are called spectral invariants. And we already saw an example of this when we were dealing with the vibrating drum problem, where we looked at the trace of the heat symmetry group. We just took the summation from e to the negative lambda kt. That was a smooth function on the positive reals. And then we looked at the asymptotic, we looked at the behavior of that function as t approaches 0 from the right-hand side. And we saw we got this nice asymptotic expansion, which told us that the volume of our domain was encoded in the spectrum, and the length of the boundary was also encoded in the spectrum. So it turns out that that's not just unique to planar domains. It's something that's true for all Riemannian manifolds. So, so I guess for any Riemannian manifold, you can consider trace of the heat semigroup which once again is just e to the negative 1 k t. And as we saw before, this is a smooth function. On the positive reals, and the observation is that if I look at this as I let t approach 0 from the right-hand side, we get an asymptotic expansion. And so the point is these guys here are what are known as the heat invariants. Okay, so if I have the spectrum of the space, I get some infinite sequence of numbers that's determined by that spectrum. Okay, but we actually want to do some geometry. So what we're hoping is that these numbers actually carry some geometric content. And so the answer is that, okay, well, actually, these things do carry content. So one can show this fact is that the K heat invariant is actually equal to this interval where u sub k and g is a universal polynomial in the curvature tensor and its derivatives. So the takeaway here is that these numbers are actually carrying local, they're averages of local geometric content. Okay? This is an average of local geometric data. Okay. So what one might hope is that okay, these things carry enough information where you can start to actually put them together to prove results about what's actually encoded or which types of manifolds actually turn out to be isospectral form, so equal determined by the spectrum. So let me give you guys a couple of examples of that. So I guess so it turns out that A0, well, this is a nice one in that it turns out this first guy, u sub 0 is just 1. And so this gives us the volume of your space. So when this tells it any two spaces that have the same spectrum have to actually have the same volume, which is exactly what we saw in the case of a planar domain. Okay, this next one turns out to be the average of your scalar curvature. And so scalar curvature is a function of space, which is kind of telling you about how volume of balls differ from the curvature volume of balls in Euclidean space. So maybe I'll just back up for people who have geometry or Riemannian geometry course. All these different curvature tensor, all these different notions of curvature are trying to get at how does the geometry of the space you're considering deviate from Euclidean space. So the Riemannian curvature tensor, which includes what's known as sectional curvature, is actually talking about how GD6 in your space spread as compared to GD6 in Euclidean space. So GD6 in Euclidean space, one way of measuring that is by looking at the circumference of a radius, circle of radius r. So pick a point and move out in all directions for distance r, and then compute the length of that. Okay, we know that that's 2 pi r. Now, if you do the same thing in a Riemannian manifold, pick a point and then move out distance r in all directions in the two-dimensional plane, you'll also get a circle, but that circle might not be of length 2 pi r. And so the point is that you can now write out sort of a Taylor series expansion for that, and you'll get that it's 2 pi r minus some other term. And that other term is what's known as sectional curvature. And so sectional curvature then is measuring, okay, up to third order, how does this length of this curve deviate from the length of a curve in Euclidean space? And then similarly here, for scalar curvature, we're doing the same thing for volumes of balls. So here, okay, this is nice, but then in particular in dimension 2, scalar curvature turns out to be the same thing as Gaussian curvature. And then from your curves and surfaces class, you'll remember, okay, there's this great theorem about integrating Gaussian curvature over space, and that was basically given by the Euler characteristic. So here in dimension 2, you actually get that this thing is going to be equal to 2 pi over 6 times the Euler characteristic of your surface. So in dimension 2, we have this nice, really strong relationship between the spectrum and the underlying space. So any two surfaces that have the same spectrum have to be the same underlying topological space, at least what I'm talking about beforehand. But I guess the bad news is that, so these first two heat invariants have sort of reasonable geometric interpretations. But as one starts to compute higher and higher heat invariants, well, you run into two problems. Well, one, that they start to kind of defy reasonable geometric interpretations, and two, they also just become really hard to compute. So actually, there are only really explicit formula for, let's say, A0, A1, A2, and A3, and sorted for A4 as well. And the ones after this don't really have, the nicest of, well, interpretations. So here, maybe this one's not so bad, but so here, for the second one, we get this expression where I'm just taking the norm of the curvature tensor, the norm of the Ricci tensor, squaring this, and then adding on 5 times scalar curvature, integrating that. And then for A3, there is an expression, but it's actually fairly long, and I guess it starts to become even more inscrutable. And so as you go up in these numbers, you get things that are kind of hard to compute. But nevertheless, the point is we want to sort of use these quantities to piece them together to prove some positive results about the spectrum and its relationship with manifolds. So I guess what we wanted to do was to talk a little bit about how one might use these to sort of study this problem of what's going on with like spaces I would call spaces that have like large symmetry groups. And so in geometry, one might expect that a space with a large symmetry group plays a very special role in geometry and physics, and my hope that role is reflected in the spectrum. So, So, I guess here's a theorem of Berger, and then later on by Tano. So I guess let MG, and NH be Riemannian manifolds. Of dimension between 2 and 5. Well, then one can show that this space in G has constant sectional curvature K, if and only if H also has constant sectional curvature K. And so one can prove this using the heat invariance, and I guess we'll do the proof in dimension 2 just because there's only a couple of lines. But doing it sort of in higher dimensions actually becomes a little bit trickier. So
what's the relationship between MG and NH in the statement?
I'm sorry?
What's the relationship between MG and NH?
Oh, I'm sorry. I didn't say, thank you. With the same spectra. Yeah, crucial. Then it turns out that one is a constant sectional period, if and only if the other one is a constant sectional curvature K. All right. So then, so the proof is really to do the following. So, in dimension 2, is to notice, okay, well, here, sectional curvature is just equal to Gaussian curvature. And so it's a function on our space, and so therefore we can just integrate it. So what I can do is for some surface, I can integrate this quantity over the surface. And the point is I'm going to get a polynomial, degree 2, whose coefficients are heat invariants. Okay, so if you work this out, you'll get the coefficients are going to be given by A0 and A1. And so then the point is given is the degree 2 polynomial, whose coefficients are given by these heat invariants. And the point is, okay, well, if this space actually has constant sectional curvature K, well, that means it has to be a root of this polynomial. But then, since these spaces have the same spectrum, well, they have exactly the same polynomial. So if one is satisfied with the quantity K, the other one also has to have K as a root, showing that they both have to have constant sectional curvature K. So that's that, and that's going to make us the easiest argument for proving something's positive in spectral geometry, and all the other ones turn to be significantly more involved. So I guess maybe the question they want to pose then I guess it's sort sort of, I guess, generalizing this a little bit more. So, okay, what I should say here, so I did note this is by Berger and Tanos, this is like back in the 70s. And to the best of my knowledge, nothing is actually known about this in higher dimensions, or it certainly is not a complete answer to this problem in higher dimensions. So it's maybe a testament to, here's maybe one of the most straightforward natural questions one can ask. Let's say, is constant sectional curvature actually spectrally determined? And we only really know that in dimensions 5 and lower. I think there's a partial result in dimension 6 or something like that, but in general, we don't really know. So I guess the question or the problem is the following. Well, suppose is a locally homogeneous space. Modeled on a geometry XG. So I'm saying this just part for people in the audience know what I mean by model geometry. But here, by a local homogeneous space, I just mean a space where any 2 points on the manifold have neighborhoods which are isometric to one another. So if you're like spheres as a locally homogeneous space, tori are locally, flat tori are locally homogeneous spaces. So if you're standing at a point, you really can't tell one point from the other. And I guess then suppose that in H has the same spectrum as MG. So then we want to ask, well, can we conclude that an A in H is locally homogeneous? So somehow local homogeneity is something which is captured by the spectrum. B, let's suppose the answer to this question was yes, the local homogeneity is captured. Okay, well, it turns out, why do I not explain what I mean by being modeled on geometry? Well, okay, every local homogeneous space has to be modeled on some geometry. So you can then ask yourself, okay, well, does it also have to be modeled on the same model geometry? Okay, and let's suppose the answer to that question turned out yes. Then the next thing you might ask yourself is, well, are NH locally isometric? So NH and NG. Okay, and then finally, you might ask, okay, well, are these guys actually isometric to one another? Okay, so it turns out that like so in dimension 2, where we know, let's say, constant curvature spaces are determined by their spectra, at least up to a universal cover. All of these questions sort of collapse down to the same question. But in higher dimensions, these things start becoming a little bit more subtle. In particular, if one goes into high enough dimensions, all these questions have the answer no. But it turns out, let's say that in dimension 3, it seems as if there might actually be the possibility for getting some traction on this problem. So, in the last couple of minutes, I'll just explain that. Well, okay. Now, this, just explain 3, it turns out that there are 8 model geometries, which I've listed over here according to this first column. So the first column represents the geometry. And this one here, this contains, let's say, your flat spaces. This one here contains your constant curvature plus 1. This guy here is your hyperbolic guys. All right, and then there are these other more general ones over here. And okay, if you're used to, let's say, from three-manifold theory, you're dealing with Thurston geometries. Okay, the Thurston geometries are sort of sub-geometries of these. These are what I'm calling metrically maximal geometries. So these geometries give you the largest collection of locally homogeneous metrics you could possibly have on your space. And so you might ask, okay, well, to what degree can you actually go through this set of questions that I was outlining over there? And so, okay, so there's a missing fourth column, which is the property of being locally homogeneous actually captured. So, okay, don't have anything to say about that right now, but if we sort of assume that we're within the class of locally homogeneous spaces, we can actually start to ask the last 3 questions and actually make some progress. So here, we're looking at the space, so E2 tilde, this is looking at the isometry group, the universal cover of the isometry group of R2. Okay, that's a 3-dimensional group. It can act on itself by multiplication. It turns out that's an example of what I call ametrically maximal geometry. And if I look at these spaces which are modeled on that, so if I start with something that is modeled on the space, well, then any other locally homogeneous space which is has the same spectrum as it also has to be modeled on that geometry. It also turns out they have to have exactly the same universal cover. And if they're flat, it turns out it's uniquely determined by its spectrum, unless it turns out to be what's known as tetra or di-di. So there are these 2 unique isospectral flat manifolds in dimension 3. They're, okay, well, called Peter Boyle and Juan Pablo Rossetti, they call them tetra di-di. So I didn't think they did. Okay, and then otherwise, we don't know. Okay, so here, that's one thing. So here, S3, S3, this is looking at S3, which is the unit sphere, so just think of it as unit quaternions. That's a group, so we can look at the space of left invariant metrics on that space. So this geometry sort of encodes all of that and all possible quotients of S3, equivalent to left invariant metric. Well, okay, so it turns out if I am one of those guys, and there's some other locally homogeneous space, which is isospectral to it, it turns out, okay, yes, that thing also needs to be modeled on this geometry. And if the metric I start out with is close enough to positive sectional curvature, we can conclude that they have the same universal cover. Otherwise, we don't really know what to say. And then similarly over here, if it has a constant positive curvature, then we know that they are actually uniquely determined, and that's the result from Berger and Topology. Here for hyperbolic manifolds, so the answer is yes, yes. Well, yes, yes, and okay, there are lots of examples of isospectral pairs of hyperbolic spaces, so you can clear this. And actually, in this case, okay, if you were hyperbolic, well then, okay, those are actually separated from all of their spaces. So anything that's isospectral to a hyperbolic manifold has to actually be hyperbolic.
Excuse me,
yes.
can you give an example for an isospectral pair of that H36?
Oh, well, okay, I don't have it off the top of my head, but there are lots of examples. So like Alan Reed, for example, has lots of examples of these. Yeah, so I'll give you some references. Okay. So let's see. Here we have H2 cross R. So this is the hyperbolic plane across the real line. And so here we're looking at the kinetic identity of that. And the answer is yes, yes, and then you can have examples there. And here are these examples. The ones that we know are ones that kind of arise by, there are lots of examples of hyperbolic surfaces, which are isospectral, and you just quotient, you can take the product of a circle. So it could be an interesting question, okay, are those the only way of getting isospectral examples in that setting? Over here, oh, that's not an S, this is an S2. So we can look at the sphere cross line, and so then in all these cases you get the answer yes. Here, this is the Heisenberg group, and so for all these guys, all the answers are yes. And then where we're having the most trouble, I guess in this case, is SL2R and Sol. And those geometries, yeah, just because of the method of proof, it actually gets a little tricky what to say there. But at any rate, I guess the things are, so to give credit to my collaborators, so some of the circle in red is work that was done with Ben Schmidt, I'm sorry, with Michigan State, and then Samuel Lin, who's currently in the University of Oklahoma. And so those are the things that we were able to do sort of recently in an article, and the other things are things that were done by others, but it's kind of credit. But anyway, so this is a problem that for people who sort of like the, I guess, intersection of geometry, analysis, and things of that nature, might have some